Gruesa. Well, that's the way we say hello in Switzerland. Hello, children. How are you people doing? I'm Saurabh Kumar Dutt, and I'm here to teach you people a little bit of mathematics. Now, children, have you ever seen a place where a river flows between two lakes? Yes, this is Interlaken in Bern, Switzerland, where River R flows between Lake Thun and Lake Brenz. Make sure to take a boat ride in either of these two lakes. Do some paragliding, windsurfing, mountain climbing, or probably some outdoor excursions. But don't forget to do two things which are quintessential. The first being have a cheese fondue, and the second being to wish any person of Switzerland that you get to see a big gruesa. In this note, children, I'm going to start off this lecture of differentiation, where we're going to look up how we employ the quotient rule. First, we will look up what the quotient rule is, after looking up what differentiation is, and then we will look up a simple sum and then a little complicated sum. So make sure you attend the whole lecture and make yourself perfect in this topic. So let's get started. Now, children, first I'll be discussing with you people, what do you understand by differentiation? For that matter, let us say that we talk about a function f of x, right? And if you want to study the change in the value of this function f of x with respect to the change in the value of the independent variable, then we call this process differentiation. For that matter, if we want to write this as a definition, we write this as limit delta x or change in x tending to 0. If you talk about the change in the value of the function, that is y or fx, with respect to the change in the value of the independent variable, you call this process differentiation. Now, this is better written as limit h tends to 0, where h represents delta x or change in the value of the independent variable. Then we have f of x plus h, from which f of x is subtracted, and then that is divided by h. Now here, children, like I told you, h is just like the change in the independent variable. For that matter, if we try writing this h, we can write it as x plus h, which is a later value of the independent variable, from which the earlier value x is subtracted. As such, h comes out to be the change in the value of x, or in other words, x2 minus x1, which can also be written as delta x. Now, if we talk about f of x plus h, we know that this is a later value of the function in x, or in other words, we can say that that is y2. And if we talk about f of x, then that is actually the earlier value of the function, or here we are talking about y2 minus y1, or in other words, delta y. So thus here we come to the old definition, that is, we are talking about the change in the value of the function, that is y, with respect to the change in the value of the independent variable. Now, children, quickly discussing all of this, if suppose we talk about a function which is f of x, it can be an algebraic function, an inverse trigonometric function, a logarithmic function, or probably it can just be a trigonometric function, right? Then if you talk about differentiating the function, then that is actually trying to find out the value of the change in the dependent variable with respect to the change in the independent variable, when the change in the independent variable is infinitesimally small, right? So this is better written by limits if we talk about h to be the change in the value of the independent variable, and now f of x plus h. From this, we subtract f of x and we divide this by h. Now, if suppose we talk about h can be written as x plus h minus x, and x plus h is the later value of the independent variable, from which the earlier value, that is x1, is subtracted, or in other words, we can say that this is delta x. Now, if we talk about the numerator is from the later value of y, or the later value of the function, if we subtract the earlier value of the function, or in other words, this is y2 minus y1, and thus it can be written to be delta y, right? So here, as we talk about this, we come back to the old definition, that is delta y upon delta x, when delta x is tending to 0, or in other words is infinitesimally small. And children, this is what differentiation is as a process. Now if we talk about the formula for the quotient function, right, that means if suppose we have d upon dx of say f1x divided by f2x, where again these can either have an inverse trigonometric function, or probably a logarithmic function, an algebraic function, a trigonometric function, or probably an exponential function, then if we talk about the ratio of both of these, and if you want to differentiate it, then that will become equal to the second function which is there in the denominator times of the derivative of the function which is in the numerator, and from that we subtract f1x times of d upon dx of f2x, and in the denominator we have f2x whole square. Now here children, this being the formula, we're going to employ this in doing sums, and I'll quickly discuss this once more with you. So if we have the quotient formula for differentiating functions, that is if we talk about d upon dx of f1x divided by f2x, so here we have f2x d upon dx of f1x minus f1x d upon dx of f2x divided by f2x whole square, right? So if you talk about this, this is known as the quotient formula, and in the quotient formula what we have is we have here few sums which have to be discussed. So the first sum that I have for you people today is if f of x is equal to x plus sine x upon x plus cos x, then we've got to find out the value of d upon dx of f of x. So quickly give this a try, after which I'll be discussing the sum with you people. I'm giving you 10 seconds for trial, right? Right guys, now let's discuss the sum. Here in this question we've been given if f of x is equal to x plus sine x upon x plus cos x. So as you see that this is actually a quotient function where in the numerator you have the function f1x that we discussed earlier, and in the denominator you have the other function which is f2x. Now if we talk about d upon dx of this given function f of x, then obviously we are to employ the quotient rule, which gives us that if we talk about d upon dx of some f1x which is divided by f2x, that is one function in the numerator divided by another function in the denominator, then this formula is f2x times of d upon dx of f1x, and from that is subtracted f1x times of d upon dx of f2x, and this is whole divided by the square of the function in the denominator, right? So employing this formula now, we will now have here d upon dx of this function which has been given to us to be x plus sine x, which is divided by x plus cos x, will become equal to the denominator, that is x plus cos x, which above we've named as f2x, times of d upon dx of the function in the numerator, that is x plus sine x, and from that children is subtracted the numerator, that is x plus sine x, times of the derivative of the denominator, that is x plus cos x, right? And in the denominator children we have the square of the denominator, that is x plus cos x whole square. Now further we have to simplify this, so there are a few more formulae that you should be knowing, which I'm quickly going to write. That is, if you talk about d upon dx of sine x, and that children is cos x. And then the next formula is if you talk about d upon dx of cos x, then that is minus sine x, right? And further children, there's another formula that we will be using, that is if we talk about d upon dx of some x raised to the power n, where x is a variable and n is a constant, then that becomes equal to the constant n times of x raised to the power n minus 1. So using these formulae, now we are going to get to the end result. So as such, here we come to the derivative to be written as x plus cos x, which will remain to be as it is, multiplied outside, and then inside the derivative of x will become equal to 1, and that of sine x will become equal to cos x, right? Further, we have here to copy x plus sine x, which we will copy obediently, right? And then further, we will multiply this with the derivative of x plus cos x. For x, it will be 1, and for cos x, it will be minus sine x, right? And now in the denominator, we have the square of the denominator, that is x plus cos x whole square. So for the children, this can then be written after multiplication because we require to simplify this. So we have now the product of two binomials, which will give us x plus x cos x and plus cos x plus cos square x. And from that is subtracted x minus x sine x and plus sine x minus sine square x, right? So in the denominator, as we already had, we have the square of x plus cos x, right? So this is it. Now children, we will further try and cancel off some terms which are identical and share opposite signs. So we have x plus x cos x plus cos x plus cos square x, and from that is subtracted x. To it is added x sine x, as minus gets multiplied with minus to give you plus sign, and from that is subtracted sine x, and then we have minus minus plus sine square x, right? Now this is whole divided by what we divided earlier, that is x plus cos x whole square, right? Now further after this, we can now write this as, we find that x and x cancel each other, and after that we have here x cos x, which remains to be as it is, and then further children, we have here to it added x sine x, which remains to be as it is. Then we have plus cos x and minus sine x. And after that, we have one interesting entity, that we have sine square x plus cos square x. And I'm sure you people must be knowing that if we talk about sine square x plus cos square x by square trigonometrical identities, we know it as 1. As such, in its place, we're now going to substitute 1. Right? And so to it we have 1 added, and all of that is divided by the earlier denominator, that is x plus cos x whole square, right? So for the children, this can now be written as x, which can be taken common outside, right? And we will now have x times of cos x plus sine x, and except that we have to it added cos x minus sine x, and to that is added 1, and in the denominator we have x plus cos x whole square, and that children is the further final answer, as we cannot further simplify this. So now quickly discussing the sum. In the question, you've been given that you've got to find out the derivative of the function f of x, which is x plus sine x divided by x plus cos x. So this is a sum which shows you the application of the quotient rule. So if you have the ratio of one function f1x to another function f2x, then the formula goes like this: the function in the denominator times of the derivative of the function in the numerator minus the function in the numerator times of the derivative of the function in the denominator divided by the square of the function in the denominator. So applying this rule to this given question now, we have x plus cos x, which is the denominator, times of the derivative of the numerator, which is x plus sine x, minus x plus sine x, which is the numerator, times of the derivative of the function x plus cos x, which is the function in the denominator, divided by x plus cos x whole square. Now next here what we do is, if we talk about x plus cos x, it remains to be as it is, and then we write the derivative of x plus sin x. Now the derivative of x raised to the power n is n times of x raised to the power n minus 1. So when we talk about differentiating x raised to the power 1, then we will have 1, which is the value of n, times of x raised to the power 1 minus 1, that is x raised to the power 0, or in other words it becomes 1 into 1, that is 1, and that is why we have this 1 here. To it is added the derivative of sin x, which is cos x, and from that is subtracted x plus sin x, which is the numerator times of the derivative of the denominator now, that is x plus cos x. Now the derivative of x is 1 and that of cos x is minus sin x, as that is another formula for you people, and in the denominator you have the existing denominator, that is f2x whole square. Now for the children, we try and simplify this. So first we've got to multiply this. So we get x plus x cos x, then we have cos x plus cos square x, and then we have minus x minus will stay outside, and then we have x minus x sin x, and minus sine square x. Now children, next what happens is, we have, when minus sign gets multiplied inside, we have minus x plus x sin x, and then further we have minus sin x and plus sine square x. Now plus x minus x gets cancelled, and then x cos x and x sin x get added up, having x to be common outside, and inside we have cos x plus sin x, and further then we have cos x minus sin x, which will be written as it is, and then as sine square x plus cos square x is equal to 1, so as such the sum of both of these can be written to be plus 1, and that then will become your final answer. So is everybody clear about this? For sure. Very good children. Now after this we will be discussing the next sum, that is this. Quickly give it a try. I'll give you 10 seconds for trial, after which we'll be discussing the sum. Okay children, discussing the sum. Now here we have, if x times of 1 plus y in root plus y times of 1 plus x in root is equal to 0, then you've got to show that dy upon dx is equal to minus times of 1 upon 1 plus x square. Now children, there is one thing to note about this equation which has been given to you, that is x times the root of 1 plus y times the root of 1 plus x. This is known as an implicit function, right? And in an implicit function you cannot separate the dependent variable and the independent variable. As such, you can't make the dependent variable the subject of the equation, as you normally have in simple equations, where you get y to be equal to some function in x, like x squared plus 3x plus 4, or probably x plus sin x, as you had in the last case. So this is a case where you won't be able to separate x and y, or in other words you won't be able to make y the subject of the equation, right? So whenever you have such a sort of an equation, there is a method with which you deal, that is, you differentiate the whole equation, and then when you get y, then the derivative of y is written as dy upon dx, and if you have a function of y, then it is dealt with as you normally deal with the functions of x, right? So at the moment we will try and deal with this question not by using this as an implicit function, but somehow such so that we can remove it to be an implicit function. So let's see how. Here first what we do is, we have this equation where we will take one term to one side and the other term to the other side. So writing the solution of this sum, we now have x times of root of 1 plus y, which will become equal to minus y times of root of 1 plus x. Now further what we do is, if we talk about squaring both the sides, then the roots will get removed. So next now we will be squaring both the sides. As such, we have now x square times of 1 plus y, as the square root and the square will get cancelled, minus minus will become equal to plus, and then you will have the square of y, which is y square times of 1 plus x. Now further children, what we do here is we will now multiply the monomials to the binomials, and thus we will have x square plus x square y, which will become equal to y square plus xy square. Now we keep the terms which are square and have only one variable to one side. So as such, we have x square minus y square, which is equal to xy square, and minus x square y, which is the term x square y taken to the other side of the equation. Now on the left hand side, we can write this as x minus y times of x plus y, as we know this, that if we talk about a square minus b square, we can write it as a minus b times of a plus b. Further now, next what we do is, on the right hand side, we find that xy is common. So we take this xy common outside, and inside we have a y minus x remaining. Now, if you talk about x minus y, it cancels y minus x minus 1 times. As such, cancelling this minus 1 times, now you are left out with x plus y to be equal to minus times of xy, or in other words, x plus y plus xy is equal to 0. Now what we can do is we can keep the terms with y on both the side, on one side, that is y plus xy, and take the other term, that is x, to the other side. Now if we take y to be common outside, we will have 1 plus x inside, and then on the other side we have minus x. So as such, now we can make y the subject of the equation as we normally can in an explicit function. So it will become equal to minus x upon 1 plus x. Now since here we have a normal equation, now further we can differentiate both the sides. So on differentiating the above equation, we will now have dy upon dx, which will become the derivative of the variable y, which will become equal to the denominator, that is 1 plus x times of the derivative of the numerator that you've just studied in the formula, and from that you'll be subtracting the numerator, right, which is minus x times of the derivative of the numerator, the denominator, that is d upon dx of 1 plus x, and in the denominator you will be having the square of the denominator, that is 1 plus x. Right, so further here children, next what we can do is, obviously you also have a square here, so this will become 1 plus x, which is multiplied with the derivative of minus x, that is the constant minus 1 will come outside, and the derivative of x will also become equal to 1. As such, it will just remain to be minus 1, and then you'll have minus minus plus x times of the derivative of 1 plus x, which will become equal to 0, as the derivative of a constant is 0. So this is another formula, that is, whenever we talk about any constant, its derivative is 0, right? So here, as such, the derivative of a will become equal to 0, and then we'll have here x times of the derivative of just x that we can write, because the derivative of 1 has become equal to 0, and 0 is additive identity, so there's no point writing it, and in the denominator we have 1 plus x whole square. Now further, when we multiply this minus sign inside, we have minus 1 minus x and plus x, which is divided by 1 plus x whole square. So here plus x minus x gets cancelled as they're identical, but they share opposite signs. So then you'll have minus 1 upon 1 plus x whole square, and that children will become the final answer. And if we try and match it, then we find that this exactly matches with what we've got to bring, right? And therefore this stands to be proved. So now children, I'll just quickly discuss this once more, so that if there is any ambiguity whatsoever, all of that gets cleared. So in this question children, you've been given that there is a function equation, which is x times of root of 1 plus y times of root of 1 plus x, which is equal to 0. And this is an implicit function because here you won't be able to segregate y and x, or in other words, you won't be able to make y the subject of the equation. And here you got to prove that dy upon dx is equal to minus 1 upon x square. So there is one thing to note here, that if you can somehow make y the subject of the equation, then on the other side you can get it all in terms of x, right? So here what we do is we try and convert this implicit function to an explicit function, which is possible in this case, and it is not necessary it will be possible in all the cases. And that is the reason why it is a little complicated that I'm discussing this sum, so that you don't have any problem in it. So we have now the second term taken to the other side. So as it is with plus sign, it will go to the other side with minus sign. Then we square both the sides so that we can remove this square root. So when we square, we will have x square times of 1 plus y to be equal to y square times of 1 plus x, as the square and the square root will cancel each other. Next, then we multiply these monomials to these binomials. So we have x square plus xy to be equal to y square plus xy square. Now we keep the terms which are with one variable, that is x square and y square, to one side, and the other terms are taken to the other side. So we have x square minus y square, which becomes equal to xy square minus x square y. Now the first term, which is on the left hand side, and the second term form a duo which can be written as a square minus b square, which is a minus b times of a plus b, which you studied in algebraic identities in junior classes. So as such, we can write this as x minus y times of x plus y. And in the other two terms, we find that xy can be taken common outside, and as such you are left out with y minus x inside. Now x minus y cancels y minus x minus 1 times. Now why so? If we talk about, say, some a minus b, right, and let's say you take minus sign common from this, then this will become equal to minus a plus b. That is because a didn't have minus sign, and when you multiply it with minus sign, it will come back to a. And because b had a minus sign, it let that minus sign go outside, and now it has a plus sign. Okay, now if you talk about this binomial which is written inside, obviously it can be written as a minus times of b minus a. So if you try and cancel a minus b with b minus a, then you'll be left out with minus 1, as you can understand from here, because a minus b can be written as minus times of b minus a. So this is what we've done here. We've cancelled x minus y with y minus x, and that goes minus 1 times. Now this minus gets multiplied with xy, and we take this xy to the other side, and thus we have x plus y plus xy. Now we keep the terms with y on one side, that is y plus xy, and take this x to the other side, making it minus x. So further now, taking y to be common outside, inside we are left out with 1 plus x. We take it to the other side, and now thus y becomes equal to minus x upon 1 plus x. Further now, as we now have this like an explicit function where y is the subject of the equation, so in this special case, now we can easily differentiate and get the derivative only in terms of x, as we require in what we have to prove, that is minus 1 upon x square. So as such here, now we require to differentiate this so that we can get to what is required to be proved. That is, we require to bring in dy upon dx somehow. As such, we differentiate this above equation. On the left hand side, the derivative of the function y will become equal to 1, and as it is a new function, because we are differentiating in terms of x, so that's why we will have 1 times of dy upon dx, or just dy upon dx. And on the right hand side, we will then have 1 plus x, which is the denominator, times of the derivative of the numerator, minus numerator, that is minus x, times of derivative of the denominator, that is 1 plus x, divided by denominator square. Remember, here we are using the formula that you learned just now. That is, if you talk about d upon dx of f1x divided by f2x, then that becomes equal to the denominator f2x times of the derivative of the numerator, that is f1x. minus f1x times of the derivative of the denominator, that is f2x, divided by the square of the denominator. So using this rule, we have done this. So as such, now next what we do is, after applying this rule, now we write the derivative of minus x, which becomes equal to minus 1, as the derivative of x raised to the power n is n times of x raised to the power n minus 1. And then we talk about finding out the derivative of 1 plus x. 1 being a constant, its derivative by the formula will become equal to 0, because the derivative of any constant is 0. And then we write the derivative of x, which becomes equal to 1, right? Multiply it with minus minus plus x, that is, it just becomes equal to x. Now ahead we have minus 1, which is to be multiplied with 1 plus x, that becomes equal to minus 1 minus x. Plus x minus x gets cancelled, we are just left out with minus 1, and that is divided by 1 plus x whole square, that is denominator square. And children, this is what we were required to show for the value of dy upon dx, and thus this stands to be proved. So are you all clear about this? For sure? No ambiguity? That is no confusion? That's good, children. Now tell me if there is any confusion whatsoever. Do write it in the comments, and I'm sure to answer back, and I'm sure to also solve your problem. But make sure now that the sums of differentiation are properly practiced, right? And if they are asked in exams, especially this question, you're able to do it really well. So bye, children. Have a nice time, but also do some maths. Bye.